how did Boltzmann define entropy? How did he make this connection between the microscopic and the macroscopic world? And also introduce this notion of temperature in the microcanonical ensemble. So I'll skip some of the steps, but I'll tell you the basic ideas. Okay, so let me then come to the definition of the microcanonical. Collection of microstates where each microstate has n particles, collection of microstates with each microstate has n particles and occupy a volume V. And I said that the energy of the microstate is E, one given value. But experimentally you are never going to measure E. I said that N, V and E, these are measurable quantities. They define the macrostate for you. So you say that NV and energy doesn't have a very precise value, but it has a value which is spread over a very small range. And if you have a way to measure energy with infinite precision, you just put delta equal to 0. So this is just a general setup. You can easily recover the case where E has a precise value by just putting delta equal to 0. So then this gamma E, let me define this quantity gamma E. So see, I defined the density rho QP. Let me just define let me just write down what I had previously. So this is going to be the density of phase space points corresponding to a microcanonical ensemble. So we had said this is equal to constant if h of, so earlier I had written, oh the mic is not right, that's why you should have told me. Some people complain that on the YouTube the sound is not audible. Now the red light is on. Okay. This is okay, or I take a new battery? Okay, so this is constant. So before the tea break, I had written that this QP, this has to be equal to E. But now that I have allowed for a small range of possible values of E, so I say that this is equal to constant if your energy lies in this range. And well, if delta is equal to 0, then you recover the earlier situation. This is just a more general situation. And this is 0 like otherwise. So now you may wonder what is not the total number of microstates, but the total region in the phase space which is going to be occupied by microstates that satisfy these conditions. Okay, this is the density. Okay, so that's trivially given by integrating this rho QP. Just see how sorry. So rho QP dq dp, and if I plug in that thing, so what I am going to get is this is equal to dq dp, provided qp are such that hqp lies in this range. By definition, what I am trying to do is I am trying to find out the total volume of the phase space occupied by the allowed microstate. So, what I have to do is that I have to integrate this. I want to know the total volume. So, by definition it is rho qp dq dp, the whole thing, but then because of this thing, so this integral, the limits of the integral is the limits are going to be restricted to the region where hqp, or I am integrating over that region of the phase space that satisfies the condition hqp lies between E and E plus delta. So this has, so let me just say this is just volume in gamma space occupied by the microcanonical ensemble. What I mean is it's the volume occupied by the allowed microstates, canonical ensemble. This is clear. See, this constant, it doesn't matter because I can absorb it in normalizing it, so it's just some constant, and I choose that constant in such a way that this is my gamma E. Then in some sense this is, one should not think of it as the number of microstates, but you have these points which are distributed in the phase space, and this is the volume over which they are restricted to move around. They cannot leave this place. And now comes the definition of the entropy. You will see in some books, for example, in Carson Wang, they say you can define a quantity called sigma E. I mean, just to, it's just a small thing. So this is the volume of the phase space with points that satisfy hqp less than E, and then it is obvious that what is this gamma E, that is equal to sigma. Can somebody tell me, this is like the cumulative distribution, that you take care of all points which are there up to E, and this is this gamma E is what? Number of points with energy lying between E and E plus delta, and this is all points up to E. So, can somebody tell me how does one write gamma E in terms of this sigma? E plus sigma E, right? And typically when I say E and E plus delta, typically delta is a quantity that has a magnitude much smaller than E. On the scale of E, it's just a small. You can put it equal to 0 if you have if you have a way to measure the energy with infinite precision. So delta is much smaller than E, and therefore I can do a Taylor expansion and retain the first order term, and that allows one to. I tell you why I did this thing, where what is omega E? This is just the derivative of sigma with respect to E, right? I mean, this I did not do anything, this is just a Taylor expansion. Why I did this is that it allows you to define something called the density of states, the number of, well, it's not number of energy levels, but it's just the derivative of the allowed phase space volume per per unit energy interval, density of states of the system at energy E. In the quantum setting, I mean, it's much more easy to see, but it's basically just that. Okay, so now I come to the definition of the entropy. So you recall what was one of the motivations for going to, or in why did one want to do invoke a statistical mechanical description of the system? Because the idea was to try to explain the laws of thermodynamics. In thermodynamics, you deal with macroscopic quantities, measurable quantities. And if you recall, it was a phenomenological theory that you had some observations, some experimental facts, and you organized them into some logical structure, and that gave rise to the first and the second law of thermodynamics. And now, our aim was to be able to explain those laws and observations, laws of thermodynamics, entropy, and so on, in terms of the microscopic details. And at the microscopic level, what I am given is a system with a certain number of degrees of freedom, Hamiltonian, Hamilton's equation. Okay. So till now, what we have been able to do is to characterize the system just on the basis of the fact that the number of particles is n, V is the volume, E is the energy. So these points are microstate, phase space. These points are going to move around, and I have told you what this macroscopic observable. How can one determine this macroscopic observable in terms of the phase space density rho? So now this was the brilliant step taken by, and I would request just after I do that to I'd ask Mustansid to add those historical this thing. Okay, so this was Boltzmann's definition of entropy. MANN. What he says is that this is the definition of entropy. This is how you define. At this stage, it may not be, and it should not be evident to you that this is really the entropy. This is some function. I can always, given this quantity gamma E, I can always take log of it, and that allows me to define some function which will be a function of E and V and N also. These are the three things that I have told you: number of particles, energy E, and V. Well, like energy in a small range of thing. And this quantity, this is known as the Boltzmann's constant. We will see later in the course that at some point you will have to identify this quantity. At the moment, it could have been something else, like not necessarily S, but some P or A or B or C, whatever, whichever is your favorite letter. But it turns out that if you identify this with the entropy of the system, the same entropy that we had defined using the second law of thermodynamics, that it's a state function that depends on only the thermodynamic parameters: volume, temperature, volume, total energy, etc. It will, as we go along, it will turn out that if you define this, identify this to be the entropy, identify this with the entropy of the system, you can recover those laws of thermodynamics that I had that I told you about. And as soon as I say that this is entropy, let's take this attitude that from now on this will be entropy, because we know, in anticipation of what we are going to show later in the course, this is really the entropy. And if this is entropy, can one of the students tell me that why this would be wrong? Dimension, right? You need something, right? Because log of gamma E, indeed gamma E, if you look at it, well, actually gamma E you need, now I have to go into this, maybe I should not have brought up this. Okay, see this gamma E, see from that it's a dimensional quantity, it's not a dimensionless quantity. But then you recall what we had done in the thermodynamics, I mean, we had defined entropy up to entropy with respect to a reference state. We have said that entropy is always defined up to a constant. So that constant you can, so let me just do it. So what you have to do is that, see, log of a, it doesn't make sense to take log of a dimensional quantity. You cannot take an exponential of a dimensional quantity, you have to define it. Can a student tell me why you cannot take a exponential of a dimensional quantity? Yes, exactly. So you cannot add x, if x is a dimensional quantity, you cannot x plus x square to 1. I mean, it doesn't make sense. It has to be dimension. So in principle, you need some quantity, something here that would make it dimensionless, some quantity which has the same dimension as gamma e. And look at the beauty of a log function, that what log function would do is that, suppose you have a something, some, let's say a or something, some constant. It cannot depend on E, because the E dependence I have already taken care of here. So then I can write this as log of gamma E minus log of A, and this I can call the entropy of the reference state. So I will take that attitude. In some book, in Carson Wang, what they do is that at some point they suddenly stick in this factor of 1 by h bar to the power 3n. I think there are 3n of them, which has the right dimension. So it depends on your attitude. Like one way to do is to say that let gamma E be dimensional. I have already taken care of the fact that this log has to be taken of a dimensionless quantity by saying that, okay, whatever be the constant, I can I can say that that's the entropy of the reference state. That's one way of doing it, and which I usually do in class, because at this stage there is no reason why one should introduce this factor of 1 by h bar to the power 3n, which like anyways doesn't have a interpretation in classical. So then forget about it. You just say, this is a simple strategy that you say that, look, I indeed have to have a constant, but then since this is a log, I can always write it as a sum of two terms, and that's the entropy of my reference state. I will always measure entropy of a state with respect to that reference state, and therefore I forget about that constant. And then I need to have something which has the dimension of what? How do I fix the dimension of this quantity without thinking too much? Inverse of what? No, what should have the dimension of energy? Can somebody tell me what do I need to multiply? I mean, that is possibly the fastest way to get. No, Ts, no, Ts has the, we have seen that d cross q is equal to, d cross q by T is equal to ds. So S or Q is like T of S, and Q is the energy. So therefore, kT has to have the dimension of energy, and therefore you know what the dimension of K is. This is just just a comment that this was really a big step in understanding of the a big step in the foundation of statistical mechanics. That here you see, let's look at this equation. See, on this on the right hand side, I have a quantity that is giving you information about that's based on a microscopic picture of the system, that microstates, points are moving around and so on. On the right hand side, I have a quantity that's defined in thermodynamics, that you come across for the first time in thermodynamics, where there is no mention of microscopics, and in fact thermodynamics was not, it was a phenomenological subject anyways, which was based on just experiment. So on one side I have the micro world, on the other side I have the macro world, and this is kind of I mean, if you just stare at it, I mean it's something like something outlandish, like you have a quantity on one side that is referring to the micro world, on the other end you have a macro world, and the two just happen to be, that's a definition, that's the way. I mean, Boltzmann is saying that you have to do this to make the connection. Of course, we understand you have to bring in some equality at some stage, otherwise like how to do this connection. So this is the the crucial step in the whole development of statistical physics, and one of the biggest contributions of Ludwig Boltzmann. So now a curiosity, like, has any one of you been to Vienna? Okay, so if you go to this, you have been to you have not been to. So on the so this thing is curved on the what is it called, like tombstone of Boltzmann in Vienna. So it's so now, so can you please explain this key? And so it.
There's a story that goes like this. It's S equal to K log of gamma. It is always associated with Boltzmann, and indeed this insight was the key insight, as Shamik just stressed, to what is it about a microscopic system that corresponds to entropy, and this was it. However, it turns out he never wrote the formula S equal to K log gamma or K log omega himself. The person who did it was Planck. So for many years K was called Planck's constant. That would have been very confusing. But Planck himself was very correct about it, and he went around telling people that, look, this is not to be called Planck's constant, it should be called the Boltzmann constant, because okay, maybe Boltzmann didn't write it this way, but he understood that the key point being that this gamma grows exponentially with the volume. They understood that, so that is the law. So people, please don't call this Planck's constant, call it Boltzmann constant. But of course, Planck soon had it as this constant also.
By that time, Planck had already had his. This constant was already there.
That's right. So Planck's introduced H in the year 1900, but he did not call it Planck's constant. But somehow, I don't know how these things get named, but Planck was really correct about it.
R by N, that's what you said, no? You said?
No. So all the earlier work, for instance, K as a constant was not there in the early days. Even if you read Einstein's paper on Brownian motion, there's no K there. It's R divided by N. R is the gas constant, N is the Avogadro number. Everywhere is R by N, R by N, R by N. Yeah, so I didn't answer your question.
So the constant was not there when Boltzmann wrote it. He did not write the entropy in this form.
Yeah, he did not write the entropy in this form, but let us say what he proposed was tantamount to it. I mean, he just didn't write S equal to K log omega. He did everything else. Maybe in some sense he wrote omega equal to E raised to S, roughly speaking.
Actually, while you are describing thermodynamics, you have the freedom to choose the origin of entropy. But that kind of freedom is not there when you are defining in the fashion you have just defined. So I guess the problem is that defining entropy in context of classical statistical mechanics is easy.
Defining is
you have to really bring the concept of number of cells.
Yeah. So it is ill-defined in that sense. It's defined up to an arbitrary constant.
Yeah, but
there is no way. No, there is no physical meaning of that constant.
No, but it's there in quantum mechanics.
But quantum mechanics has not yet. Of course.
That's why I'm saying, in this way of defining, it's not. I mean, it's ill-defined to define Boltzmann entropy in context of classical statistical mechanics.
No, I think it is well defined. You just say that it is defined up to a constant which is ill-defined. I mean, it doesn't have one meaning. You can. I would not bring in H bar at this stage. I mean, this is what I want to do. I want to, because if you bring in H bar, see, you started off with a Hamiltonian. You said Q's and P's are continuous variables, and then suddenly, because you have to fix some definition, then you say, oh, now there is an H bar. So that I don't want to do. It's just a question of taste, maybe. That's what you said.
So, like, here already there should be a density rho, right, to cancel the factor of dq dt.
No, rho I have already taken into.
That constraint
Yeah, that constraint is not in some sense, it is in all sense. I mean, I am getting it just because I inserted that expression for rho.
Delta function,
Huh.
there would be a delta function sitting inside the integral to cancel the dimensions of q and
No, because there was a delta function that I got, there were two delta functions. One,
Delta function, what's the dimension? It's 1 over
Yes,
energy.
yes, I'm
It's
saying
not
that
all the q's and p's will not be taken care of.
One over energy.
Delta of E minus
This is
energy,
D3 and Q.
it's just 1 over energy.
no, this is of course G3 and Q, and because I said that Q is Q1, Q2, Q.
if the rho is there,
Huh.
the
Rho
will
is,
have a dimension of 1 by dq dt, right? Rho.
If it is normalized to 1.
yeah.
Yes. So normally you will have something like rho there, right? To cancel dq dt. Because integral of rho over some volume will give you the number of measure of microscope. So that will, like, this gamma will turn out to be a dimensionless value. You have rho there. It should be there.
Let me see how does it work out. So I said rho of QP is equal to constant if H lies between E and E plus delta.
But the dimensions of that constant is 1 over q and p, like 3n times, right? Because rho dq dp should give us the number of microstates per unit volume.
The total volume occupied by, okay. Yeah,
This is dimensionless, right?
yeah. This I can call it to be 1, okay.
So there should be a rho, and you have to integrate over a volume in the phase space. I'm saying that gamma e should be a number.
Okay, let me see. So what I had done was I had done this, and then
If you integrate over a volume.
okay. So let's do it carefully. I think it will not, but I may be wrong. Okay, let's do it. QP of dq dp. So let's say this turns out to be some c, some constant, and therefore I say that rho QP is equal to 1 over c, right? So 1 over c if H between E and E plus delta and 0 otherwise.
Is C dimensionless?
No, it shouldn't. It shouldn't be.
Yeah, it
Because we define density as number of microstates per unit volume in phase space. That per unit volume in phase space carries the dimensions of
no, just 1 minute. Rho is defined as number of points per unit volume. Per unit volume, but per unit volume goes away.
yes.
So this is a constant.
If you put rho there, gamma will be just a dimensionless number.
Oh, I see. Okay, okay. Because C is dimensionless. That's what you're saying. C is dimensionless now because C is dimensionless because she is dimensional because rho is the way I have defined rho is the number of points per unit volume, and per unit volume and this volume goes away. So this is just a number, and so therefore 1 over c is a number, and so okay, I see. Okay, okay. So well, again I think the point is that okay, this number of points per unit volume. So then again you are invoking number of points, but that's probably it's okay. I mean it cannot be counted and so on. Okay. So
Algebraic is not consistent. Is it the same C in both places?
C is
Take the right hand side expression, put it into the equation. What will you get?
sorry, which one?
Yeah, you have C in two places.
Huh.
There and on the
Huh.
left. Is it the same C? You are writing rho as proportional to 1 by C. Integral of rho is proportional to C. Is it the same C?
It should be no, because I want it to be normalized to 1. So therefore, if I do dq dp integral, okay. So in that sense, yeah.
Actually, there should be a distribution function, like because there is a value of e.
Hmm.
So it's like two uniform is like ret function, right? Ret function, step function, unit step function. The subtraction of two unit step function will give me a uniform be within a finite range, right? That should be in rho itself.
Yeah, but that does not carry any dimension.
No.
Delta function carries dimension.
Delta.
But here it's a product of two step functions. Theta of h minus e times theta of e plus delta minus. The product of two step functions. Step function carries no dimension.
I think instead of doing it this way, what I can do is that I can call this to be 1 and then rho has a dimension. Because then if I do it, can somebody figure this out? It's just a question of bookkeeping, like what you are doing here.
C divided by the viscous volume. If you normalize it in this fashion.
If I normalize it this way.
Yeah, that way. That's the integral.
No, suppose I normalize it this way. Rho has some constant that.
Yeah, it will be 1 over the viscous volume.
Okay, so this will be 1 over gamma e. Right?
That's fine.
Then it's fine, right?
This definition, yeah. This
Okay, so then it's fine, because then if I do it this way, if I do integral of this, by definition I will get a gamma e in the numerator and that cancels it. Okay, so it's normalized to 1 with this definition. Okay, so let's do it this way. If I define this to be, so first of all this is going to be a constant, that's for sure. And so what I do is that if I choose rho qp to be this one, then you see that with my definition of gamma e, rho qp is normalized to 1. It's normalized, sorry, dqtp is normalized to 1, but now rho qp has the dimension of what? So gamma e has the dimension of phase space volume. So that's why you will have that same problem, that
Yeah, but my question is the correct way of interpreting. Actually, maybe in the book of Lambda or somewhere else, it's mentioned that defining entropy statistical mechanism in uniform quantum mechanics. Because for measurement purpose, it's fine.
It's fine.
That constant will go away.
Yeah.
We have to ultimately take the difference.
Yeah, exactly.
But for proper interpretation, you require quantum.
Acha. So like with that
And
precaution.
for sure, I can, in case of black hole, this is one of the reasons why people are thinking of quantum.
Okay. So with that,
Sure.
okay. So yeah, okay. But still, I would not like to do it. I know that there is a problem. So let me put it this way. At this stage, let's not bring in h bar. I can put in, okay, let's put it this way. You need some quantity that has the dimension of qp to the power 3n to make it dimensionless. You can do it this way. Let's not call it h bar, because no, I think the point is that, of course, there is this thing as to which one is correct and so on. But also, I think while teaching in a class, see, quantum mechanics comes a bit later probably, as far as I know. So I think if you just I somehow feel that this sequence of steps is kind of could be misleading to some students, that you started out with a classical system, Hamiltonian and classical equations of motion, and suddenly you say, okay, you can say it has to be some constant which has the dimension of qp to the power 3n. And it turns out that h bar is one such quantity, but let me call it something. You can call it something else. That's one way of doing it, or the other way to do it is to say that, like, anyways, s is equal to k log gamma. So whatever constant I put in here, that I can subtract away, because I will be interested in. So let's just fix this thing once and for all, because since this is mainly for the teacher. So which one are you comfortable with, or which one do you usually do in classes?
All teachers were students at some point of time. I found it very odd that suddenly it was an imposition. Why leaving the age? And it was justified and rationalized. Okay, we will learn that later. So overall, looking back, it might be very consistent to put age there. But in the logical progression of things, as and where a student stands, not having an age would be more consistent. But of course, later he will look back and justify an age.
I think the way one says it is that ultimately the world is actually not classical, it is quantum mechanical. And by taking a limit, you can recover classical behavior. But when you take that limit, there a 1 over h to the 3n.
Okay.
That is his argument, but it is to invoke something which is not natural in classical mechanics. Maybe a halfway thing is to put in a constant which has the correct dimensions and not tell people later we will find it.
Depends on how finicky the student is. Also.
No, but
If the student is a purist, he might have problems. Otherwise, it's okay.
No, in most cases, the student is not quite aware of. No, see the way. This is, I feel that the way you guide, you are going to, the students to a large extent depend on the teacher, like the way that he.
Then honesty is a lonely word.
So if I have to be like honest, I say that well, there is some constant that you need. You don't put it here, but then you need to put it just to make that definition make sense. That log of this, but anyways, that can be set. You can. We have learnt in thermodynamics that you cannot define the absolute entropy of a state. Second law of thermodynamics doesn't allow to define the absolute entropy of a state. It allows you to define the entropy with respect to a reference state. And what I can do is that I can call whatever constant I put in there, log of that is the entropy of that reference state. And we can say that later on we will see that actually later on here we are building the foundation. Later on we will see that we have to use either Fermi-Dirac or Bose-Einstein or Maxwell, which is the limit in which you get classical. Maybe this is the best way, I don't know.
Right. I think it's okay. I mean, maybe you can say there is a constant just to make it dimensionless, so that you can take a log. And we will find
Okay, so let's do like that. That since to Boltzmann, to make sense out of Boltzmann's definition of entropy, so log of so I need to make this thing dimensionless. So I put in something, let me call something some a to the power 3n, where a has the dimension of h bar. It could be h also. H. It has the dimension. I did not say that that's equal to h and h bar. Of course, have the same dimension. H is sufficient. Okay. So now with that definition, so before I move on to define the to define temperature in microcanonical ensemble, I just want to just show you the steps of how one may go about computing this quantity, this volume of gamma space occupied by the allowed microstates for a simple system of a classical ideal gas. Okay, just show you some steps to you will realize that indeed this quantity or sigma e that I had written, it grows exponentially with the number of degrees of freedom. It turns out that you can do this calculation exactly only for a classical ideal gas for which the particles are non-interacting. Okay, so it's just it's there in Wang, but I'll just show you how to what's the number and so on, not show you how to. See, let me make another comment. Like another reason why I don't want to put in this factor of h bar is that it might give the students a feeling that you need quantum mechanics just to make sense of this expression. It's not like that. It just turns out that that has that dimension. You don't need quantum mechanics because of this. I mean, if you just put in this factor, you'll say, oh, okay, so therefore it's quantum mechanical, we are doing approximation and so on. You don't need quantum mechanics. I think that's correct. Right? You don't need quantum mechanics to make sense out of this definition of entropy. You need it for different reasons. Or you don't need this thing because you want to make a sense out of black holes and so on. I mean, that will come later, and then for consistency you need to put in the right factors. So what is a classical ideal gas? So I want to just show you the steps because it's pretty straightforward to tell you, how does this quantity sigma E look like for a. So like as I have told you, what's a classical ideal gas? That you take a gas, any gas of your choice, and you make it sufficiently dilute, and then you find that all gases start behaving in the same manner, and that limiting behavior is defined to be the classical ideal gas. So a classical ideal gas doesn't exist, it's an ideal gas, and it's, you take, how do I get a prepare a classical ideal gas in the lab? I take any gas of my choice, I make it sufficiently dilute, and now can you tell me, one of the students, that what happens if you make the gas very dilute? What's the physical effect that's going to set in? Huh? Their interactions will become very, very weak. The particles, because if one particle is here, dilute means what? That in a given unit, in one unit volume, the density is very low. If one particle is here, the other particle is very far away, and if it's a short range interacting system, it's important to remember that I am talking, okay, for a gas the interaction is anyway weak to start out with. So for such a system, the Hamiltonian is just the kinetic energy, Pi square by twice m, I is equal to 1 to up to 3n. So I want to compute this quantity sigma E. So what is sigma E? So sigma E is, I integrate over all the P's and all the Q's. So there are 3n of them, Q's and this one. But then I have the condition that H of QP is to be less than equal to E. The first thing and the macro state is, I told you the number of degrees of freedom and the total volume and the total energy. E or E plus delta, whatever you want. Let's say E and E plus delta. So the first thing that you realize is that for this classical gas, this H is a function of only the P's and not the Q's, and therefore I can trivially do this integration over the Q variable. So each Q variable is going to reside, so that's going to give me V to the power n, I guess, V to the power n, and dp1, dp2. Why I did not get V to the power 3n? Yeah, exactly. So there are three such, and this can be, this integral, I am not showing you how to do it. It's okay, H for this system is a function of only E. This can be done, I'll not do that that derivation. So the way to do it is to think of an 3n dimensional space whose axes are p1, p2, p3 up to pn, and this H is a function of only the the vector, the length of the vector that you get in this 3n dimensional space, because it's just p1 square plus p2 square plus p3 square and so on. So you can do it in two ways, like going to the spherical polar coordinate in that many dimension. It's pretty straightforward, so I'll not do it. I'll just write down the final answer. So the sigma E, it turns out to be equal to V to the power n. E is so this is going to be E. You give me the P's and that's E. E has the same definition as you have come across in classical mechanics, right? In this case, E is just the kinetic energy, because it's a classical ideal gas. The particles are not interacting with one another. The potential energy is just not there. So this same notion that you have of like energy. H is energy for all practical terms, but H is a function of Q and P, and once you put in those values, the value that you get is the energy. So I don't know, like since you, so in Feller they do this thing, no, that x is a random variable and the value that it takes is called small x. Somehow they, it's something like that. It's not the same. Somehow they make this distinction. This is this is some up to some constant. I just want to show the dependence on n. I just want to show that this is exponential in n. So v times twice m e to the power 3 by 2 whole to the power n. So there are some n dependent constants here, or maybe this C n also depends on n. Oh no, there is this independent constant also here. What is this sigma e? What is this C3n? I think it is something like this. I don't have it. This can be worked out exactly. I think something of this sort. And you see that the number of microstates, just a classical ideal guess where there are these particles moving around, doesn't depend on E is the total energy. Sorry, yeah, E is the total energy. So E is just yeah. So you see that you get a number of or the volume of the phase space occupied by the microcanonical ensemble as something that grows exponentially with n. Like, is this clear why it is an exponential in n? You just write it as a to the power n is e to the power n log something, right? And n log, so n log of this quantity. So this is just a number, doesn't depend on n. So e to the power n times something. So the number is going to grow exponentially, explode exponentially with n. Just to show, you may wonder, what's the total number of microstates that I'll have. Like even for a very small number of particles, n doesn't have to be 10 to the power 23. Even for a very small number of particles, let's say 100, it's going to be e to the power 100 times some number that doesn't depend on n. That's a huge number of microstates that's possible. Huh? Sorry? Up to e, yeah. That's and like even if you take the derivative, you know how to go from sigma e to gamma e, that n the exponential dependence will still be there, because gamma e is nothing but del like omega e times delta. So you have to just take the derivative with respect to e, but this exponential dependence on n will remain. Maybe you will get a factor n minus 1 and so on, but n is large. So okay, so now I come to this sorry?
Gamma is gamma function of that number.
No, there is no gamma function. Oh, acha, this one. Okay, so now I should not have written gamma, but like omega for the gamma. Okay. Okay, this is a gamma function. Yeah. Gamma. Sure. Okay, yes, 3n by 2 factorial. No, very, you have to just know how to find the volume of a spherical, how to compute the volume in an n dimensional space and the spherical shell, and so very simple, like, well, Oh, I think it's there. I don't have. Yeah, it's in there in Wong or like. I probably don't have it in my notes, or probably I'll have it somewhere. So we'll skip derivation of results and so on. I think it's more important that we discuss the concepts. Huh? So derivation you can look up on internet and so on. Now what I want to do is I want to get to this concept of temperature, and you remember how we had defined temperature, not defined temperature, we have seen one feature of temperature, that suppose, well, temperature, like people knew how to define temperature. It's something that you feel, like you touch a substance and you say that it's hot, it's cold. So like at the back of our mind, somehow we had a notion of temperature. We didn't know how to interpret it in terms of microscopic details, H and so on. But temperature as a word was quite well known. And then we had seen while discussing thermodynamics that there was this thing that you take two substances kept at different temperatures, you bring them in contact with one another, and then something happened that led to the equalization of temperature, that at the end of the process the two substances put in contact with each other had the same temperature. So we want to understand that why does it happen and what is the temperature and so on within this framework of gamma and phase space and so on. Okay? This would allow us to define temperature in terms of this entropy, some derivative of entropy and so. So we want to consider that physical situation. You have two substances, some materials, you bring them in contact with each other, and then what happens? Or to put it differently, so what I would do is that instead of I'll take one substance and okay, I can do it that way also, whichever way. So, or maybe I do it this way. So I have two, so this is my system A and this is my system B. They have now been kept in contact with each other, and the composite system is isolated, because now till now, I mean with the formalism that we have developed until now, we don't know how to treat the situation in which the system is not isolated. We have considered only the case in which the system is isolated, the total energy is constant and it has some evolution, microcanonical ensemble and so on. So within that setting, we will consider the case where you bring two systems in contact with one another, or you may think of just one system which you somehow break into two parts, and then there is the composite system is thermally isolated. So let's say the system A has got, so this is my system A and this is my system B. Let's say your system A has got N1, so what kind of wall is this one? So think of the physical situation. What you have done is that you have brought two systems in contact with one another. So you would expect that there could be some energy exchange between the two, but the number of particles of each subsystem is not going to change in time, and so is the volume of each subsystem. So system A has N1 particles and volume V1, and or let's say I am using N1 V1 and this is N2 V2. These are constants. N1 is not changing as a function of time, V1 is not changing as a function of time, and so is N2 and so is V2. But what we know for sure is the following, that the energy of system A may fluctuate, the energy of system B may fluctuate, but the sum of the energies of the two systems, well, no, before I come to that, let's say that this is, let's consider the physical situation where you have taken one system, you have broken it into two parts, you are considering the left part to be system A and the right part to be system B. Okay? And I assume for the moment, and I will tell you why do I have to make this assumption, I assume for the moment that this A and B, I mean both the systems have particles that are interacting with each other only over a short distance. short range interaction. Okay, short range interaction. So instead of going into details, let me just tell you that short range meaning that every particle is interacting with only those particles which are located within a finite range of its location. Okay, it's not going to, not like a gravitational interaction or a Coulomb interaction and so on, which extends all the way up to infinity. It may get weaker as the distance increases, but there is still, you cannot say that beyond a certain distance I am not going to consider. For example, an exponentially falling distribution, you may think of it as a short range interaction. Beyond a certain distance, it's very good to say that it's a very good approximation to say that it's equal to 0. So then when I broke it up into two parts, and suppose I want to know what is the energy of the combined system. Okay, what is the energy of the combined system? So let me call it combined. So that's going to be equal to the energy of the energy of system A plus energy of system B, okay, taken separately, plus there will be a term which is coming from interactions of particles which are located in system A with those in system B. Okay, it's natural, it's I did not do anything. And if it so happens that this is the system is a short range interacting system, then what you can do is the following, that ultimately we want to study the situation where N1 and N2 they have got like Avogadro number of particles, and the V1 and V2 they are also very large. So finally we will take the limit when N1 is very very large, V1 is very very large, N2 is very very large, and V2 is very very large. If so is the situation, then in that limit I can forget about this term. Why I can forget about this term? Because first let us understand that this term is going to be proportional to the surface, right? Because these are short range interacting particles, so it's not that a particle here is going to interact with a particle there. Okay, this is not possible. Only those particles which are here, like lined along the surface, they are going to interact with those along this so this other side of the surface, and this is the contribution that is taken care of in this term by this term EAB. Like as I make the system larger and larger, like make volume V1 and V2 larger and larger, the surface to volume ratio is going to go to 0. Okay, it's like what is a good example of it's not going to work with what is a good example of surface to volume ratio? Sphere, huh? A cube, okay. Sphere will also work. That if you draw a sphere of this length, okay, the surface and volume they are comparable. But if you think of a surface, a sphere which is so big, see this, the surface will have contribution, the surface contribution will come from just the surface. But there is so much in the bulk, so much amount in the bulk, that what I can do is that in the limit in which I will consider V1 and V2 going to 0, so this term, these two terms will dominate over this term. Okay.
The surface volume grows as radius cube.
Okay. So that's also. Okay. Yeah, the surface, what he is saying is that volume will go in d dimension as r to the power d, while surface is just the derivative. So it would go, think of 3 dimension, v goes as r cube, while the surface goes as 4 pi r square dr. So it's proportional to r to the power d minus 1.
So the ratio is 1.
So this is, it's not that when the volume is increasing that these two guys stop growing, they also grow, but they grow at a much faster rate than this one. Or to put it differently, if you divide out by volume, you are going to get a quantity which is surface by volume. Okay, this will be volume by volume which is of order 1, volume by volume which is of order 1, but here you will get a quantity which is surface by volume, which in the limit of a very very large system will be negligible. So I can forget about that contribution. So then I say that the energy of the combined system E combined is equal to E1 plus E2. That's the energy of the first system and that's the energy of the second system. And of course, it doesn't tell me the precise values of E1 and E2. It just tells me that there are many values possible for E1 and E2. That satisfies, there are several values possible. They all will be consistent with this definition. Yeah, so a tutorial and a lecture is okay, but 2 lectures probably.
Yes.
Okay, so taken separately, like suppose I tell you for the system 1, so suppose system 1 is, you consider it separately, it has nothing to, it's not in contact with system 2. Then taken separately, the system 1, if I tell you that number of particles is N1 and the volume is V1 and the energy is E1, you can at once write down the entropy of the system. So that's going to be equal to E1 V1 N1. That's equal to K log of gamma 1 E1, according to what we discussed till now. So this is the total volume occupied in phase space by the allowed microstates. By the way, I say that the whole system is in microcanonical equilibrium. The whole composite system is in microcanonical equilibrium, and I allow energy to be exchanged between the two systems. I don't want particles or the volumes to be these systems are not allowed to exchange particles between them, or this guy, the partition, I don't allow it to move around, it's fixed in space. Okay, the number of particles is also fixed, but what I allow the two systems to do is that they can exchange energy among themselves. So E1 and E2, they can have many different values, all satisfying this constraint. Taken separately, that's the entropy of the first system. Taken separately, you can write down the entropy of the second system. K log of gamma 2 E2. But now what I am asking is the following, that I want to write down the entropy of this composite system in terms of these two quantities. I think I call them S1 and S2. So I have two systems, they are allowed to exchange energy among themselves, and what I want to do is that I want to write down the entropy of the composite system in microcanonical equilibrium in terms of the entropy of the two subsystems taken separately. Okay. So that I don't know whether one has to do it or request some doing. So that I claim it can be written out like this. So of course, so before I write down this thing, so what is going to happen is that just with those constraints, N1 V1, N2 V2, E1 E2, you may think of many different microstates which are possible for system 1 and system 2, and they will all be consistent with those conditions. The only condition that I have to keep in mind is that I am going to consider all microstates for system 1 for which the energy is E1, and therefore the system 2, for system 2 I will have to take care of only those microstates for which the energy is E combined minus E2, right? That is clear, because the energy of the two system, the sum of energies of the two system is a constant. So I have to take care of those microstates of system A for which, let us say, the energy is E1, and this will have an energy equal to E combined minus E1, and now I sum over all possible values of E1. The numbers I can like easily take care of the number of particles, because anyways the number for this system is a constant, it's not allowed to fluctuate. The volume is a constant, it's not allowed to fluctuate. For this system also the number is a constant and the volume is a constant, it's not allowed to fluctuate. In this particular situation, what I am allowing is this system to have many different energy values, and this system also may have many different energy values. The only condition is that the E combined, the energy of the first system plus the second system, it lies in a given range E and let us say E plus delta. Is this clear? That for the composite system I have defined for you the macro state. The total number of particles is N, the total volume is V, and the total energy lies between E and E plus delta. Okay. So, that is for the composite system. And since the number of particles in each subsystem is a constant, so you can say N is equal to N1 plus N2, V is equal to V1 plus V2, and E combined is equal to E1 plus E2. Now, since the two systems are allowed to exchange energy among themselves, I will have to take count all microstates which are possible for A with energy E1 and all microstates which are possible for B with energy E combined minus E1, sum over all possible values of E1. So this, well, I kept on saying number of microstates. What I am after is really the volume of the accessible gamma space. Okay, it's not really number. It will be number if you deal with discrete variables. So this is once I write it down, it will be clear. So in case this okay, so let us look at it. So gamma 1 and gamma 2. So gamma 1 gives the let me for for this part of the course use the word number of microstates. So that is the number of microstates possible for system 1, and for every possible microstate of system 1, system 2 may exist in many different microstates. There is nothing that forbids it to exist in different microstates. The only restriction is that the sum of the two energies would have to be equal to the combined energy that lies in that range. So that is what I have done, that this gives me the number of possibilities for system A, and this gives the number of possibilities of system B, and you see that if you add the two, so let me call it, this is combined, and this, okay, and I have to sum over all possible values of EI, and if you want I can do it, but basically one way to do this thing is to somehow discretize the energy spectrum. I mean, for this one you have some energy values, and this delta, it gives you the discretization step. Okay, you can do it in more than one way, but it basically you don't have to. Please don't. There may be more than one ways of doing this discretization, but what you should remember or what you should appreciate is the fact that there are many microstates which are possible for system 1, there are many microstates possible for system 2, but then I will have to take care of only those microstates for the combined system for which the energy constraint is satisfied. That is it, and that is why I have a sum over many different values, and this is going to give me the allowed gamma space volume for the composite system. You will see that the same thing, here I am like allowing like energy to exchange between the two systems, but this same setup can be used to also take care of the situation or to consider the situation where let us say the energy is constant, but I let particles go back and forth between the two, or let us say somehow I like allow this partition to move this way, and that would lead to volume exchange. The volume is not constant for each and every, for the two individual systems, but the sum is constant, okay, in this setting.
Will it also mean that
No. So, in this setting what I am doing is that at one time I am keeping two variables fixed and letting one quantity change. You can generalize it, but at the moment let us stick to this one. But so forget about number and volume because it might sound confusing. We will consider those situations later. But I hope this energy exchange part and this thing is clear, right? How this discretization is done in Carson-Wong, there is it's very simple. I mean like so physically it is like straightforward that this delta, this imprecision, it allows you to discretize the system because you don't know what is happening in between E and E plus delta. That's a level of precision or resolution. Yeah, resolution is a better word. But now let us look at the entropy of the composite system and see what do I get, and we'll get some interesting results. Sorry? You can write it as an integral also. I was doing it like discrete steps, like 5 here and 6 there. I pick one from there, one from there. You can do it as an integral. But the point is that, I mean, either you have an integral or a sum. Like in any case, you are going to get not just one contribution, because like as is clear from the picture, there may be many microstates possible for this one and many possible for this one. I have to take care of all those that satisfy this constraint. So let's look at the entropy now of the composite system, which by definition is k log of gamma E. And then if I just plug that in, what I get is a k log of summation over I equal to 1 to E plus delta E combined plus delta. So from now on, instead of writing combined, I'll just write EC, just to make life simple. So gamma 1 of EI, gamma 2 of E minus EI. So the next thing to do is to note that this gamma 1, this is a positive number because it's a volume of a, this is the allowed volume of the phase space, and so is gamma 2. So this is a log of product of two positive numbers, and there are some E combined by delta, certain number of positive, it's a sum of positive terms. So let's say that in this sum, you are somehow like able to identify one particular term in this sum that's maximum, like 1 plus 5 plus 8 plus 7. So 8 is the largest term in the sum. What I do is that for a given system, I write out all the terms and I select the term that that's the maximum, that gives the maximum contribution in this term. And so let the largest term in the sum be gamma 1 of E1 bar, gamma 2 of E2 bar. I don't know what E1 bar and E2 bar are. We'll find out what they are, but I know for sure that E1 bar and E2 bar would be such that the sum E1 bar plus E2 bar would have to lie in that range, EC. Okay. And remember, delta is much smaller than E. It could be put equal to 0 or it's much smaller than E. So then I see this equality. Okay, so let's look at this term. So this is a sum of E combined by delta number of terms, and obviously if I replace this sum by the contribution by the largest term, I am going to get a number which is smaller than S. Okay, sum of several positive terms. So, I have picked out one. So, the number that I get is going to be less than this whole sum, right. So, let me just single out that particular term. So, that term will be k log of gamma 1 E1 bar gamma 2 of E2 bar. Okay. So, this number is definitely going to be either less than or equal to E of E, because I have singled out one term. And also, if I replace each term in this sum by this maximum term, then of course I will be like overestimating it, because this is by definition the largest term. So, there will be, by definition there are other terms which are smaller than that. It could be that all the terms are the same, or it could be that the other terms are less than this. So, this, so let me put it here. So, this, so what's the, if I replace each term in this sum by the contribution from the largest term, so what do I get? I get k log of E combined by delta times this, right. So, that will give rise to two terms. So, one is k log of gamma 1 E1 bar gamma 2 E2 bar, that is one E2 bar, that is one contribution. The second term will be k log of E C, E combined by delta, because there are that many terms. So, what I have done is that I have replaced each term by the maximum term, and therefore, this is the inequality that I will get. This is an just a reflection of the fact that I am dealing with, and if there is a degeneracy, that is already taken care of, that it could be that all the terms have the same magnitude, and that is already taken care of by that equality there. Now, let us do some order of estimate calculation. Let us look at the dependence of each of the terms in that inequality on the number of particles. Okay. So, we have already seen that this gamma 1 and gamma 2, they are going to grow exponentially with n. Okay. Gamma, sigma, we saw that sigma is like something to the power n, which is e to the power n something. Okay. So, let us write it like this, that log of gamma 1, that is going to be proportional to n1. Similarly, log of gamma 2, that is going to be proportional to n2. There will be some contribution here, it could be some n dependent contribution, but this is the leading n contribution in the large n limit. While what is E? EC, so that is the energy of the combined system. Okay. So, this is a short range interacting system, and I will not have time to talk about long range systems, but for a short range system, you have every particle interacting with only a finite number of particles, I mean those which are located in a finite range around it. So, if you have n particles, you can think of the total energy of the system as n times the energy of every particle, because every particle is interacting with only a finite number of particles. So, this E C is going to be proportional to the total number of particles in the system, and that is n1 plus n2. Similarly, E1 will be, so let me just write it, it is just proportional to n1 plus n2, while E1 will be proportional to n1 and E2 will be proportional to n2. It turns out that for a long range system like gravitational and Coulomb and so on, this this linear dependence is not there. The energy grows super linearly with the number of particles, with the number of degrees of freedom. One should not say number of particles, number of degrees of freedom. And if you want to know more about it, you can, in the library we have kept a book on reserve, or you can talk to me in private, but I just don't want to get into the details of this one. While delta, see, delta is a constant that is independent of the number of particles. It has nothing to do with the number of particles in the system, it just depends on the resolution of the instrument that you have employed to measure the energy of the system. It has nothing to do with that. Okay, so delta is a constant that's independent of n. So let's now look at that expression. So you see k log gamma 1 E1. So let me just expand this thing. So k log gamma 1 E1. So there is this thing here. Similarly, this thing there. So in terms of S1 and S2, what I get is S1 of E1 bar. Let me not write the dependence on N1 and V1. So those are understood, okay? Or let me write at least on, okay, it is not. Less than equal to S of EV, less than equal to S1 of 1 bar plus S2 of E2 bar plus there will be this contribution k log of EC by delta. So now what I want to do is in the next step I want to write out the dependence on the number of particles, and let's see, so how does it look like. See, if you do that, you know that E1 bar is going to be proportional to N1, E2 bar is going to be proportional to N2. So if you write that out, you will get some constant times N1 plus some other constant times N2, maybe not A times N1 plus B times N2 less than equal to S of EV. So this A and B, they don't depend on N, they depend on they depend on other quantities, and then on this side you will have the S1 E1. So this is A N1 plus B N2 plus here what do I have? I have a quantity that's logarithm in EC, but EC is what? It will be proportional to N1 plus N2. So then I have a term which is of order log of n, log of N1 plus N2 if you want. Let me, sorry? Log of? Which is N1 plus N2. Because see, these two systems, they are not allowed to exchange particles among themselves. Okay? So n is equal to N1 plus N2 and V is equal to V1 plus V2. Okay? Now what I do is that I divide throughout by n. So let me just do that. So I do this, I do that. I don't know what I not do it. N is equal to N1 plus N2. I am not writing. So as you make N1 larger and larger and N2 larger and larger, N, remember, is N1 plus N2. So you get a number which is of order 1 here, right? This is also a number of order 1. So is this one, so is that one. While here you have a number which is log of n by n. This doesn't grow so fast, like log of n, it doesn't grow so fast as n. So like as you increase, as you make larger and larger, as you make n larger and larger, this term is unable to, this log n is unable to keep up the growth that's there due to n. And therefore, in the thermodynamic limit where n1 and n2 become very large, you can neglect this term. This term will no longer contribute. It will just give rise to some subdominant contribution.
So in fact, if n is, let's say, 10 to the 23,
it is already by 10 to the power 23.
divided by 10 to the 23.
So this is the bad thing about log. So log, it's a very slowly growing function. Just to tell you one story, if I am not wrong, like Landau had a scheme where he would rate physicists on the logarithmic scale, and therefore it would be very difficult to someone to gain prominence in his frame, like, because log of 10 to the power 23 is 23, it's only 23. Yeah, something like that.
Rated Einstein as half. And it was a
Yeah.
that way scale.
Huh.
Bigger.
So I think this is you understand, exponential is a very fast growing function, and logarithm is just consistent, because so therefore what is going to happen is that as n becomes larger and larger, you have an equality of this form, that a less than equal to some quantity. So let me call it the s, the s quantity, let me call it s, small s. So a less than equal to s less than equal to a plus a very small quantity that you can neglect, and therefore s is equal to a. It's in the limit in which n1 and n2 become very larger, in the limit in which n1 goes to infinity, n2 goes to infinity. Or if you don't want to divide out by n, you can think of it this way, that there is this axis, somewhere here is the, you can think of it this way, that there is this axis, this is somewhere is SEV, and this is the left hand side and this is the right hand side. As n increases, this one will move, this one too will move, but at some point both will move at the same rate, right, because this term becomes negligible, and therefore s has to be the, I think the best way to do it is look at it is this way. For some reason Carson-Wang doesn't do it this way.
No, but you should divide, because it's the entropy
Per particle, which is entropy density, which is just as you talk about, when n goes to infinity and volume goes to infinity, you don't quite talk about the number of particles, you always say density of particles, number of particles per unit volume. So here is this step clear? So this thing is not there in Carson-Wang, so that's why I am doing it. All these calculations, these are pretty straightforward. Like I'll come to the okay. So today the time is okay. So I'll come to the physical interpretation maybe tomorrow. But just understand this thing, that also in deriving, in arriving at the fact that s has to be equal to a, we have explained, and also in the previous part of the derivation, we have used the fact that it's a short range interacting system. That's why I could say that the energy of the composite system is the sum of energies of the individual systems, what is known as the additivity principle, okay, which is not going to work for long range systems. And what do we do? So does it say that okay, the whole formalism is going to break down for long range systems? It doesn't say like that. You have to do it carefully, more carefully, and it can be done, and if you are interested we can discuss it, but not okay. So at the end, I mean, what is the final result that we get? So the final result that we get is kind of very interesting and revealing. Tells me that so what do I get? I get S of E of V, the quantity in between, that's going to be equal to S of E is equal to S1 of E1 bar plus S2 of E2 bar. I don't even know how to compute at this stage. I mean, I'll tell you, it's a simple thing, but I'll tell you in the next class. I don't even know how to compute E1 bar and E2 bar, but it just tells you that the entropy of the composite system is the sum of entropies of the two subsystems, like evaluated at some special values, E1 bar and E2 bar. And what are E1 bar and E2 bar? These are the values of E1 and E2 for which the entropy of the composite system is maximized. We will come to the physical interpretation tomorrow. So,
E1 bar plus E2 bar is not necessarily
no, this is equal to E, so you can write it. Yes, indeed. So that's why this leads to the definition of temperature, but we'll come to that tomorrow. But so in case you have some time in the evening, please go through the not the way you discretize and whether it's an, these are trivial things, but it's important to understand this fact that you have a composite system and you are trying to make a list of microstates which are allowed for the composite system in terms of microstates which are allowed for the two individual systems, and I can write it as a sum of positive terms, and then a magic happens only if the number of particles is very large. If the number of particles is just 1 or 2, you have to deal with that sum. You cannot do any of the, but like any, yeah. So let me just leave it at that. So Sumsa, can we make that like announcement for the announcement of the books? We put a book this one. How to? Let me just.
Well, no, so as you know, registered practice